So, in this lecture we will learn about graph searching. So, graphs for us is a collection of vertices and edges, and we need to explore the vertices in a certain order. Let us take a simple example. If you think of any social networking site, you can look at your individual page as a certain node, and you want to know all your connections. So, you want to know who your friends are, their friends, and so on. So, you can think of this as a huge graph in which each person is a node, okay, and there is an edge between two people if they are friends. Okay. So, you have given some such graph. So, here there is an example of 4 people, 1, 2, 3 and 4, and here 2 and 4 are friends with each other and they are friends with 1 as well. Okay. So, you have given some arbitrary graph. How do you look at all the vertices, list all the vertices in a certain order, okay, restricted to, let us say, I mean, if you think about the case of social networking sites, you want to order all your connections in some order. Okay. You can either look at, I mean, you can look at your friends, list them out, and then friends of friends, and then friends of friends of friends, and so on. And that would essentially be what we will refer to as breadth first search. You can also look at an alternate approach. You find one of your friends, look at another friend of his, and keep on doing that sequence of friends, then you will get what is called as DFS. Okay. The commonly used searching techniques, they are, we will just write them down: breadth first search and depth first search. Okay. So, here if you start your search at vertex 1, we may view vertices 2 and 4 are the vertices at depth 1, and the vertex 3 is at depth 2. So, if you look out at the order 1 followed by 2, 4 and followed by 3, that would be the breadth first search. You have listed them in the order of their depths, that is called as a breadth first search. Whereas, if you list it as 1, 2, 3, 4. So, you have gone from 1 to 2, from 2 you could go to 4, from 4 you could go to 3. Okay. But there are examples where these two searches return different orderings. Okay. So, let us look at this more formally. Let us first look at a little more complicated example. So, we have the following graph. Okay. Suppose we have this graph. What will the BFS ordering be, and what will the depth first search ordering be? Okay. So, we will first write down the BFS ordering, starting at vertex 1. So, the start vertex, let us color it using red. This is just to indicate that it is a starting vertex. Okay. So, that will be the first vertex that is encountered in BFS or in DFS. And now, look at all the neighbors of 1. There are precisely 2 neighbors, 2 and 3. List them out, you will get 2 and 3. Okay. And the next stage would be to list out all the neighbors of 2 followed by all the neighbors of 3. To do that, in this case the neighbors of 2, there is 3. So, we will not list out the already listed neighbors. So, there are precisely 2 neighbors, namely 4 and 5. Okay. So, 4 is a neighbor of 2 as well as 3, but 5 is a neighbor only of 3 and not of 2. Okay. And then we will list out neighbors of 4 and 5, and we will get 6, 7, and then we have the neighbor 8. Okay. So, this would be the BFS ordering. That is, if you take the DFS ordering, so let us say, so in BFS ordering it is not it is not fully determined in the sense did we visit vertex 2 before 3 or do we visit 3 before 2, that is not really specified. You could visit in any order, and that has a chain of other choices that may not be fully determined. Okay. The same applies in DFS. Which neighbor you pick, there is no restrictions in either BFS or DFS, but whether you look at all neighbors of a node and then go to the next level, or whether you keep on traversing the graph layer by layer from one vertex to its neighbor and then to its neighbor and so on. So, that is what differentiates BFS and DFS. Okay. So, DFS ordering from, so you could go from vertex 1 to vertex let us say 3, and from 3 you could go to 4, from 4 you could go either to 5 or 6. So, the ones which we have visited we will just draw in red. So, 1 to 3 we went, and from 3 to 4 we went, and then 4 to 6 we could go, and from 6 we could go to 8, and from 8 we could go to 7, and from 7 we could go to 5. And after we have reached 5, we see that all its neighbors are essentially visited. Okay. So, the neighbors of 5 are 3, 4 and 6, all of them are visited. So, you go back to the node from where you came to 5, namely 7, its neighbors are all being taken care of, same with 8, same with 6, same with 4, you backtrack all the way up to vertex 4. 4 has a neighbor which is not yet visited. So, that is node number 2. So, that will be the last node that is visited. Okay. So, this will be the DFS ordering. Okay. So, now we will see how we can algorithmically implement this. We will see an algorithm for BFS doing these searches. What we will do is the following. We will have colors associated with every vertex. So, these colors is to indicate whether certain vertex has been visited, whether all its neighbors have been explored and so on. Okay. So, we will have 3 colors. So, colors will be one attribute, another attribute would be its predecessor, each vertex will have a predecessor. So, this will indicate the vertex from which we explored the given vertex. Okay. So, if you have a vertex u, so u dot color will initially be white for every vertex. So, this is the start state, every vertex will be initially white. The other colors are gray and black. Gray would mean we have partially explored that vertex and it is still under process. Some of its neighbors have been explored, some of them have not been, and black basically means all its that vertex, everything that we had to do with respect to that vertex is over. We have finished the processing of that particular vertex, and there will be another parameter associated with each vertex, that will be its predecessor. So, we will denote it by u dot pi. So, u dot pi would mean the predecessor of u, and this is the vertex from which we reached vertex u. So, that will be the predecessor of u. Okay. Now, our algorithm, the way it works is, it will have a queue, and we will push these vertices into a queue as the algorithm progresses, and after the all processing is done, we would have visited all the vertices from a given starting vertex. We will assume that the initial graph that is given to us is an undirected graph, which is a connected graph. Of course, BFS would work even if the graph was a directed graph and if it was a disconnected graph as well. When the graph is disconnected, what we can do is we can start a BFS at some arbitrary node in each connected component. Okay. We might need to discover what are the connected components, or we could just start BFS at every vertex of the graph. If we start this BFS at every vertex of graph, we need to check whether a certain vertex has already been covered by any of the previous BFS. So, while doing the breadth first search, if we have already seen some vertex as part of searching certain other component, we can ignore that BFS search. So, that modification can be made, and directed graphs, essentially the same algorithm would work. But for just to keep things simple, we will just look at a undirected example. Okay, so in the BFS algorithm, we have to initialize the colors. So, there is an initialization phase wherein for every vertex, so u dot color will be set to white. That means at the start, vertices are all unexplored. So, we will assume that the BFS algorithm, which we may call it as BFS, it has two parameters, the given graph and the starting vertex S. Okay. And for every vertex, the parent u dot pi will be equal to nil. So, initially we do not know what is the predecessor or parent of a particular vertex. So, we will just set it to pi. As our algorithm progresses, when a node is discovered for the very first time, the edge which caused the discovery of this particular node will be explored, and that edge will tell us what is the predecessor of the particular node that we have just now found. Okay. So, initially this is set to nil, and then we can also initialize the queue. We will call it as the queue, we will name it as queue itself, and this is set to empty. Okay. So, there is an empty queue. The queue will be used to track the vertices, and as it is initialized to empty. Okay. And then what the algorithm does is it will repeatedly explore for whatever is there in the queue. Okay. So, after the queue has been initialized, we have to add one element. So, we will add S to Q. The starting element that we had, the starting vertex that is added to the queue. It will be the first step of the algorithm, and then while Q is non-empty, we will repeatedly do certain actions. So, delete an element from the queue, so we will call this deleted element as V from Q. So, Q is a first in first out data structure, which means the element that you have added, they will be removed in the same order. So, at the start we have added just one element. So, when you try to delete, the first element that will be deleted is going to be S, and then for every neighbor of V. So, we have deleted one particular element. For each of its neighbors, we would start exploring those vertices. So, for every neighbor, let us say u of v, we will do the following. So, we have one particular node that is deleted and that might have many neighbors, and for each of the neighbor, if it is an unexplored neighbor, means no this vertex has not been explored before, we would want to do something with it. If it has already been explored, we will just leave it as it is. So, if u dot color is equal to white, in that case what we will have to do is we will have to push this into the queue, and before adding it into the queue we will change its color. So, this means we need to process it. So, we will change its color, and it is the processing has begun. U dot color is equal to gray, and its parent u dot predecessor, this we will set it to v, because v was the vertex from which we visited u, because u is a neighbor of v. Okay. So, the parent is being set, and then we can add u to the queue, add u to queue, and after this processing is done, for every neighbor we can change the color of the vertex v to black, because v has been processed. So, v dot color is equal to black. Okay. So, that is the algorithm. So, now let us see this in action. So, let us say we have this following graph. Okay. If you start at vertex 1, so this we will just maintain a queue. So, this is our initial queue, and we will first add vertex 1 to the queue. That is the only element that is there in the queue. Okay. And then we delete 1. So, initially the color of all vertices are essentially white. Okay. Once we have added, the color of that vertex changes, it becomes gray. So, 1 is now a gray vertex, and we will look at all the neighbors of u and change its color, and we will set its parent to 1. So, the vertex 1 has 2 neighbors, namely 2 and 3. Okay. So, 2 and 3, their color is being changed to gray, and the parent is being set to vertex 1. So, there is going to be, so by this arrow I will indicate the parent. So, 2's parent is 1, 3's parent is also 1. Okay. And after this, so this is the step that you do, and 2 and 3 has been added. So, we may assume that first 2 is added, and after the processing is done 3 is added. Okay. So, vertex 2 would be added and vertex 3 would be added, and we would have taken off 1 after this. Okay. So, that would have been the first step. We have deleted that element and we have changed the color of 1 to black. Okay. So, now it is no longer gray, but it has become black, indicating that full processing is over. The queue is still not empty, so we will pick out vertex 2. Okay. And if you look at vertex 2 that has been deleted, once vertex 2 has been deleted, we will look at all its neighbors. Vertex 2 has namely 3 neighbors, 1, 3 and 5. sorry, 1, 5 and 6 are the neighbors. Okay. When you look at these neighbors, 5 and 6 both are currently of color white. So, we can add them. Okay. So, let us say we first add 5 and then add 6. Okay. So, that goes inside the Q, and their color as well as parent is reset. So, 5 becomes the first neighbor, let us say it is 5. Okay. So, color is changed and the parent is set to, and 5 is added, and after 5 is added, the next neighbor of 2 is going to be 6. That is also going to change its color to grey, and we have a parent for 6 which is 2, and 6 has been added into the Q. Okay. So, after 5 and 6 has been added, the next node that you process is 3. 3 has again 3 neighbors, 1, 5 and 4. Out of them, the only white neighbor is going to be 4. So, that will be converted into grey, and the parent would be set to 3. And additionally, we would have 4 coming into the Q, and 3 by this stage is done with. Okay, we would have deleted 3. The next element that is going to be deleted is 5, but there is no further processing to be done with 5, because all the neighbors of 5 would have been already of color other than white. So, 5 is also done. So, when we are deleting, after the delete phase, after the neighbors have been processed, we would have changed the color to black. So, we have skipped a couple of steps, we would have changed 2 to black and 3 to black after that, and then 5 to black. Okay. The next node that is going to be processed is going to be 6. 6 is one neighbor, namely 7. So, we will add 7 into the mix, into the Q, and its colors are changed, and the parent is also set. 6, the other neighbors of 6 are 5 and 2, which surely cannot be added, and after 7 has been added, we can say that the processing of 6 is over and its color becomes black. The next node that would be processed is 4. 4 has 2 neighbors, 3 and 7, but both of them have colors different from white, and therefore, there is nothing to be done with any of the neighbors of 4. 4's color will be changed to black, and then the Q contains only 7, that is removed. All the neighbors of 7, namely 6 and 4, has already been processed, they are black in color, and therefore, nothing is to be done with 7 other than change its color to black. Okay. And at this stage, the Q is again empty. So, that processing is over, and we would have traversed all the nodes by that. Okay. And note that if you look at just the predecessors of each node, that will be an interesting diagram. This will be a tree. Then going to be no cycles, it is a directed tree with every node having a unique path to the vertex 1. Okay. And so, that tree is called as the BFS tree. Okay. And this entire algorithm can be implemented in linear time if you maintain the initial graph as an adjacency list. Okay. The next search algorithm that we will see is the DFS search. So, let us begin the DFS search, or the depth first search. So, again we will have two parameters associated with each node, namely its color and the parent. Okay. Instead of using a queue, we could implement DFS algorithm using a stack. We will see a recursive version of the DFS algorithm wherein we will not have to explicitly maintain the stack. The recursion would essentially keep track of the stack. Okay. So, DFS algorithm, this will require two inputs, two parameters, one is the graph itself and the other is the starting vertex. We will have an initialization phase wherein the color of each vertex. So, u dot color is equal to white and u dot parent is equal to nil. So, before you start the DFS algorithm on any particular graph, we need to do this initialization. Okay. And once this is initialized, we can call our DFS routine. So, we will write down the DFS routine, two parameters g and s. We will assume that the initialization has already been done, and what we will do is the following. So, we will make the color of S to be gray. So, S dot color is equal to gray, and then for every neighbor of S, for each we will do the following. If V dot color is equal to white. So, while the DFS is being run, each vertex its color could change. We want to ensure that the colors change from white to gray to black. So, if you have a white colored vertex, that means it is not been explored yet, and therefore, we are ready to explore it now because it is a neighbor of vertex S. And what we will do is, we will just call DFS with this new vertex, okay, on the same graph. So, DFS GV, and after all the vertices of S has been processed, we can set the color of S to black. S dot color is equal to black. Okay, maybe so at this point, just before calling DFS, we will need to set the parent V dot pi is equal to S. Okay, so let us see how this works. Okay, so suppose we have this particular graph and we start DFS at 1. Okay. So, initially every vertex is of color white and the parents, there are no parents, everything is nil. Okay. And when you call DFS on vertex 1, what happens is the color of that vertex immediately changes to gray, and then what happens is the recursive calls start. So, for every neighbor, the vertex 1 has two neighbors, namely 2 and 3. For each of them, we are going to call the DFS. Let us assume that the first DFS call will be for 2 and the next DFS call will be for 3. But before that, we need to check whether those are white. Indeed, they are white, and therefore, we can make those calls. Okay. The very first call that will be for is DFS 2. When DFS 2 is being called, what happens is, it will go into the recursive call, the recursive routine, okay, and inside that the color of this would be made gray. okay, and we would have set the parent. Okay. The parent of 2 is going to be 1, and now we are going to process DFS G with 2. When we are running the DFS on 2, its color would have been set to grey, and then for each neighbor of 2 we will have to process this particular code. I mean, we will have to process these code segment for every neighbor of 2. 2 has 3 neighbors, namely 1, 4 and 6, but out of them only 4 and 6 are white, and therefore those alone will be processed. Okay. So, let us say vertex 4 is going to be processed first. So, its parent is going to be set to 2, and while DFS G4 is being processed, this will turn into a grey node. Once this is a grey node, we will have to explore all its neighbors. It has 4 neighbors, 2, 3, 6 and 7. The white neighbors, there are 3 of them, 3, 6 and 7. So, presumably all of them will essentially be processed. Let us say DFS 4, when it is being called, the neighbor that is picked first is vertex number 7. Okay. And therefore, the parent would be set and 7 would turn grey, and DFS 7 is going to be processed. When DFS 7 is processed, 7 has 2 neighbors, namely 4 and 5. The only white neighbor is going to be 5. So, there is going to be a DFS 5. Okay. When DF and the parent is going to be set, and DFS 5, it will look at all its neighbors. Its neighbors are 3 and 7, and 3 is still white in color. So, that would be processed and that turns grey. And when you are processing 3, the only neighbor of 3 that is still in contention is 6. So, it will directly go to 6. Okay, and let us look at the situation now. I mean, 6 would have turned to grey, and all the neighbors of 6 are of color other than white. So, the call will return back to 3. Okay. Now, let us just make one more neighbor. If we had a neighbor 8, which is connected to both 1 and 2, okay, the recursive calls would have happened in the same way. If you look at 6, all its neighbors has been processed. So, you will go to 3, and 3 also every neighbor has been processed. There is no neighbor of 3 which is of color white, and therefore, it goes back to 5, and from 5 it goes back to 7, from 7 it goes back to 4, because all the neighbors of these nodes were already processed. When you come back to 2, okay, 2 had lot of neighbors, namely 6, 4, 1 and 8, but the only neighbor which is still white in color is 8. So, that will be processed, okay, and the parent would essentially be pointing to 2, and this would become grey. Okay. And at this point, all the calls have been serviced, and 8 has no longer any other neighbor. I mean, 8 does not have any neighbor which is white in color, and therefore, the entire processing is over. Should have checked that while we are returning these calls, the color is changed from grey to black. Okay. So, the place where we would have ended up our search initially would have been 6. So, at node 6, when we were at node 6, all its neighbors were processed, and at that point this would have turned black. Okay, 6 would have turned black, and then we would have come back to 3, and all neighbors of 3 have been processed. So, this would have again been turned to black. Okay. And then when the call returns to 5, this would have become black, and then that call returns to 7, and 7's call is also serviced. This becomes black, this would have become black, and the call returns back to 2. 2 has one more neighbor to be processed, 8. After 8's processing is done, this becomes black, and then 2 becomes black, and then 1 becomes black. Okay. And at this point we have a tree which is obtained by looking at the predecessor nodes, and that is what we will call as the DFS tree. Okay. This entire DFS operation, which we did via means of recursive calls, we can implement it by means of a stack. So, each recursive call, instead of it being automatically serviced by means of stack, we can explicitly construct our own stack and push the vertices into the stack and pop it out from the stack as and when those vertices are processed. So, in either case we can implement the algorithm in linear time, assuming that the graph is given in an adjacency list format. So, this is about BFS and DFS. We will stop here for the time being. So, that is the end of this lecture.